Hey there, everybody. Welcome back. This is 13.6. We're doing directional derivatives in Calculus 3. We're going to look at examples, and we were showing the directional derivative is the partial of f with respect to x times u1 plus the partial of f with respect to y times u2. As a reminder, that is the gradient of f dotted with u. It's important that you get comfortable with this gradient. It shows up throughout Calculus 3, especially when we get to endgame topics like in chapter 15. Divergence and curl both use the gradient, and we will use them to solve a lot of problems. Flux has uses in it. You see it in there, Stokes theorem, the divergence theorem. For physics, if you've got a conservative vector field, we can show it's a conservative vector field using gradients of the potential function of that vector field. There's a lot of stuff coming with gradients, so let's get used to it now. Let's learn to love it. Let's do it with some examples. We're going to start with f of xy equals x to the 5th power y squared minus 2xy. We will find the directional derivative in the direction of 3/5, 4/5, and we will do this at the point 1, 3 for this function. So I wrote this in a box just so we'd have it there as a reminder what we're doing. We need to find the partial of f with respect to x and y, and then do some evaluating. So I did that here. We've got 5x to the 4th y squared minus 2y for the partial with respect to x. The partial with respect to y is 2x to the 5th y minus 2x. Let's plug that into our directional derivative formula. So I'm just plugging stuff in there. Then we're going to evaluate. Plug in x naught, y naught, u1, u2. A bunch of work there, blah, blah. Go through it. You'll see we get the directional derivative is 133 over 5. And if we actually looked at the gradient of f itself, f, or the derivative with respect to x at 1, 3 in the x direction, the derivative with respect to f or respect to y of f in the at 1, 3, we'll get 39, 4 as the direction of the gradient of f. So as a reminder, that's the direction of the maximum slope. And so we could find the maximum slope at that point just by taking the norm of the gradient of f, or finding the finding the magnitude of the gradient of f. And so when we normalize the gradient of f, we divide through by that magnitude. This is the direction u1 would have to be, so that we were, or the direction of u that we'd have to be going in, such that we have the steepest slope. Okay. And by max slope, I mean if xy represents an overhead view of the terrain, like say a mountain range, we talked about this in the last video, the steepest uphill climb is measured by that slope in the direction of f, or the gradient of f. The min slope is the opposite direction, the path which would descend down the mountain the quickest. So remember, slope doesn't change from being rise over run. We're not, it's no longer delta y over delta x. But it does measure the amount we go up in terms of the amount we go forward. Okay? So when the slope is really high, every step we go forward along that path, along u, the direction of u, every step we take in that direction, our increase in height or contour line, as we'll see in the next section, is that slope. Okay, let's take a look at another example. F of xy, we're going to just say it's x times ey. And we're going to be at the point 2, 0. We just want to find what direction has the steepest ascent. So let's just think about that. We know the gradient of f dotted with u would give us the slope. The direction of the maximum slope would be the steepest ascent, and that's when u is in the direction of the gradient of f. So we need to get u to be the gradient of f. So let's find out what the gradient of f is there. Let's just find it out. We'll pick u to be that direction, and we can find out the direction of the steepest ascent. So the derivative with respect to x is ey. The derivative with respect to y is the original function itself. We will evaluate this at 2, 0, and we get the direction 1, 2. So the direction of the steepest ascent is in the direction of 1, 2. The slope in that direction is going to be, if we take the magnitude of the gradient of f, square root of 5. And this is effectively giving us heights. How much is the height changing? So we can use this to find contour lines, as we'll see in the next video. I want you to think about that, though. If we're doing the gradient f dotted with u, and the slope is pointing us in the direct, like the u, when u is the same as the gradient of f, it points us in the steepest ascent. And when u is in the opposite direction of the gradient of it, points us in the steepest descent. What direction does u need to be in to point us along contour lines? Think about that. Peace.